Hello, after all this time, I'm finally doing the video about the changes I made to this clutch from the K1300R 2009, this particular one. I did this video yesterday, spent all the time doing it, and then the time uploading it, and then YouTube said, too long, can't do it. And why I'm telling you about that is that I took this out of the bike yesterday, put it here, and opened it on camera to show kind of the amount of oil that was actually in here, because I've changed a lot of the oiling pattern here. Okay, so that's where we're at now. So I will open this up, but there's no use looking at the plates because I wiped them dry. But it was very adequate, and there was no, you can tell when there's wear on the pressure plate and the hub itself. In the oil, you can actually see soot, little black deposits that surround where the pads rest on the pressure plate or the hub. Just to repeat myself here, I am not an engineer. I am not a mechanic. I'm just somebody who was curious and a little bit obsessed. I went into this thing over 150 times, and the motivation for this started out on the old forum, the IMBMW. And when I started wondering why this huge clunk in this bike, and started asking questions about, oh, well, what about this? What about grooves? What about, started looking into it. Anyways, there were a few people that got very insulting, and it's one thing to question ideas, but it was quite another one to actually have personal jabs. And one of them, along the lines of one, which was, I must be somebody that believes in the flat earth. I'm so out of touch. Anyways, so there was a bit of ego that started out, but there's no way my ego would have carried me through over 150 times going into this. After that, it got into curiosity, and I just took off from there. Anyways, okay, to get into this now, the general problems here initially were viewed as not enough oil in this clutch. And that has persisted, and I believe it probably started with the K1200s. I had a K1200 and it had a horrible clunk. But it had other problems. They hadn't really figured out the proper method and amount of oil to be delivered to the clutch. There are a couple of other people that have done very good videos about these clutches and the bike in general. Patrick Hoffman has a number of very good videos, and he's an Australian aircraft mechanic, I think. And then there was an English fellow who goes on YouTube under the name of Sharelike, and he addresses some of the issues within here. And the other big one he addresses is the back of the basket, these springs, and the aesthetics. It's probably not a real issue with the operation of the bike, but that rattling sound is one of those things that can disturb people, as this clunk disturbed me. Part of riding a bike is kind of the sensory experience, and one of them is audio. And one of the first things a lot of people change is the exhaust for that sound. So, you know, the sound a bike makes can play a major part in somebody enjoying that bike or even purchasing that bike. And this clunk was something that bothered me. So anyways, back to the big thing here with too much oil. I did start out looking at things with that in mind, that, oh, there must be not enough oil. Sorry, it's not enough oil, not too much. And so I started looking at how to increase it, and very quickly, it became apparent that it was not a lack of oil. It was too much oil. And it was all fluid coupling that was locking this thing up together. So when it's spinning within the housing there, this is attached to your drive shaft. That's a lot of rotational mass, and it's supposed to break between the transmission and the engine itself, and it doesn't, or didn't. So this huge mass suddenly coming to a stop, and whack, it whacks into everything. And that contributes a lot to the wear of this thing, and also wear in the basket. Just to take this apart here, to start. Oh, what do we got here? Turn this over. Just before I start really get going here, I kind of just want to acknowledge that there are very few people, if any, that will want to do what I did, because it's kind of over the top in the amount of work, but it can kind of edify as to what's going on here. And at the end, I will kind of make a few kind of suggestions about how to approach if somebody wants to try these. So it can be a modest modification to see. At this point, I don't have the answers, but it would be worth somebody kind of having a look at. The other thing is there are probably, because I went down so many different routes kind of looking at this, and I did not have an endless source of these or the steels, these meaning the pressure plate and the hub. I had to kind of keep adding to some of the changes I'd already made, so some of these changes may be of little use or don't contribute really much at all. Let me see here. Okay, yes. So let's start with, well, just going through here. I'm just going to open this thing up and put these all aside. Here's a steel. I put some grooves in it. That was something that I did find did contribute to kind of shedding some oil. Because in the end, it really was, as far as I'm concerned, way too much oil pouring through here. Oil has a few functions. One is, of course, lubrication. Another is to wash debris out of here, because these surfaces and these pads are basically sacrificial, and they will wear down. And in the wearing down, it creates creates some debris, fine debris. And if it's not washed out, this metallic stuff becomes more and more aggressive because just more and more accumulates. If you look at Sherlike or Patrick Hoffman's videos, the very first friction plates, all of them would show that this, or the majority of them anyways, this was in between all these pads was just filled with this black gunk. And that black gunk was oil and pretty much the debris of fine bits of metallic particles worn off of this. And that just makes this, it grooves this out, it grooves out the other end. So oil can also, is meant to kind of wash things out. And the other thing is it acts as a coolant. It can flow through and carry away some of the heat that's generated here. So giving BMW the design of this, that they had an intention in this, I believe it probably comes from more of what was more important to them was not the clunk when you went from neutral into first. It was the shifting between gears, and that many people have mentioned on the forums about how the throw, when you pull the clutch in, the engagement point is just a very fine part right out at the end. I don't know what it might be, a centimeter long or something. And they wanted that extended. It's like they're not used to that. But I'm guessing, I've never raced, don't know anything about racing bikes or clutches, but the fact that you can just kind of go like this with this bike to switch gears, I think they may have, this is giving them some credit, of course, for doing it properly in their mind. So the racing part was more important. And one of the results of that is that, I hope everybody understands and has watched the other video how this works, is you've got this arrangement, and you've got a slave cylinder. When you pull that clutch in, the slave cylinder is pushing on this pin. This rides in here, this here. It's pushing on that pin, and what that does is this is attached to that. So what it's actually doing is pushing this pressure plate away. So when you pull the clutch in, this is moving out. And the idea here is that, okay, if that moves out, now there's space in between each of these, and they're free to move. The problem is it's such a tiny little space that this moves apart, that the space allotment is actually about 2 millimeters, which you can measure just looking at this steel to the top edge of this hub. This, when you push the clutch in, all these plates move, and this one you would not want it to go off of this hub, because once it comes off, it's free to spin and it could fly around in there and make a mess. So there's 2 millimeters of throw in your, when you pull the clutch in the slave cylinder. So 2 millimeters. And how many spaces do you have? You've got 16 plates here. So that means there are 17 spaces along here. And 17 going into 2 millimeters is 0.125 of a millimeter. 1/8 of a millimeter is what is allowed by that slave to create space between here. That's an incredibly small space. And this fluid coupling is really easy to happen, and everybody's experienced that with that clunk. So that was part of their, I'm just guessing, that's part of their reason for doing it as they did. To add 1 more millimeter to the throw from 2 to 3 would have made a huge difference, because fluid coupling between these two kind of pieces, a steel and a friction. I don't think, probably not enough oil here. Anyways, they can stick together. And with fluid coupling, the way fluid coupling can be broken is if you try and thicken the film of oil, it loses some of its capacity. The shear, its ability to resist shear becomes less and less. So having more space allotment between plates would have contributed a lot to reducing the fluid coupling. To break fluid coupling, as I said, you can create more space. Another way to break fluid coupling is with turbulence. And that is part of the reason why BMW kind of went with these kind of steels that have these little dimples in there that creates little tiny spaces where, yes, the fluid is thicker, so okay, you're weakening the coupling ability of the fluid, or the viscosity at that, and also add turbulence. Their standard steels used to be just pure flat. And in this case, that was even worse for fluid coupling. The other one is introducing air. So you've got increase the space, you've got turbulence, we'll break it up, and introduction of air. This is the pattern of the friction. This was the last iteration, so you can see the pads and lots of space between them. Prior to this design, they had this pad arrangement. So the pads were bigger. So the progression, you can see they're heading towards more and more, adding turbulence, or introducing more turbulence and allowing more air in that's more frequent. And here's one of the famous Barnetts. I put this in my K12, and because it had been spoken of as the cure for this, I found no difference, absolutely no difference at all. And you can see that its ability to create turbulence compared to here, or introduce air from here to here, I think there's quite a difference. Not enough to create or to eliminate the clunk, but we're heading in the right direction. So I am not going to go through the details of what I did with each steel. It's very common in, especially, well, in automotive, I think even, but especially in heavy industrial equipment. Clutch drag is an economic, or can be an economic factor in the life of the machine, because that extra resistance that the engine has to overcome over the life of these things can add up to quite a significant fuel usage, I guess. This is what I understand. So they are interested in shedding oil, getting this thing to break cleanly, so there's very little fluid coupling. They normally would do it on the frictions. I could not do that on the frictions, so I chose to do it on the steels. And there'll be a huge variety of kind of patterns here, and it depends on where it is located here. Anyways, I'm going to take this apart and go on to something else. Let's do this. Keep it organized. Oh yeah, see, okay, you know, I didn't wipe off all the oil. There's that classic fluid coupling. And this happens to be on one with no dimples. Okay, what did I do with the oil? Coming back to the oil. In the other video, this unit, as I said, would ride on here within this, and this pin, this is where your drive shaft connected to your transmission comes through, and it's hollow. And the oil is traveling up through that, and this pin that your slave is pushing against, this is way too big of a hole. This would be a very tight tolerance in here. So that sits inside there. And this is spinning, has two slots, so as I said in the other video, it's spraying oil out. So oil is coming into your hub, and as I said in the other, I'm not going to go into detail here, but it has these little channels, and in the channels there were holes drilled to deliver oil to every specific pairing of just to little environments in here. So the little environment would be, you've got your steel, there would be a hole right above that steel, and this would go on there, and then of course a steel would go on top of that. So within this little notch where the hole is, it's like its own little environment. And so whatever hole there is would oil the top of this, the underside of the steel, and then the underside of the friction and down there. So that's what's going on, how it's traveling through. It's passive, it's not an active oiling system. So with the oil here, like I said, I found there was too much oil. So what I did, and it's a long process and I won't go through every step, I filled up the original oil holes in there. And what I did was I have a kind of a Dremel-like tool like this, and I have a little ball grinder on the end, just a very small, like 1/8 of an inch or something. So I would just touch where the hole was on the inside, basically, so it created sort of like a bathysphere, those windows. So any pressure on it, there's a mechanical part to it, so it's tapered and then goes straight. But the pressure from this side, from the spinning of this thing, just added some security. The product I used to fill those holes here in North America, this is an American product, this JB Weld. It's a fantastic epoxy, and I think it says it's got like steel in it, probably some very fine particles. I chose this because it is stable up to 550 degrees Fahrenheit, far higher than this will be. Oh yeah, by the way, as I mentioned on the other video, I was waiting, or in the comments anyways, I was waiting till I did some mileage on this. This clutch, with its modification, I put about 7,000 kilometers on it, and I really could see no wear. Granted, that's not a huge amount, but it looked good so far. So, oil holes. So, I have a diagram here that I kind of set up. I'll just put it down here for the moment. And this is like this. It's as if you just cut this and kind of spread it out. The lower part here is this surface, and the upper part is on the top here. Each of these vertical lines is one of these channels that the oil is meant to flow through. Where'd my little pointer go? Oh, there it is. These channels that the oil is supposed to go through. So the bottom here is showing where the original OEM holes were. And so they, down here at the hub was an area they were concerned with. Okay, we need a good amount of oil there. And so they actually put 2 holes. Now the OEM holes were approximately, I think, a little under 1/8 of an inch. Pretty wide hole, so there's a lot of oil going through there. And then each one of these horizontal lines represents a steel, one of these steels. And so here we are in between steels, that little environment I was talking about that lives between these teeth. And you can see that it's very, very, very Germanic the way they did this. It's just the millimeters after here are roughly distance up from the hub, up this way. So 14, 20, 25, 31, 37, and 7 was down here. They did add one in between down here because I think they found that there wasn't quite enough oil to the underside of this steel and the top side of that particular friction plate. From the other video, you'll remember that there was uneven oil distribution, and most people, if they took it apart, would see it in how wet the plates are or how dry. And pretty much it's these plates that would occupy this area were really quite wet. Then they kind of went dry, and then they got a little wet again up here. And that was due to part of it was reluctance of oil just to get through here, as far as these middle ones being dry, or this portion being dry, because there was a hump. You remember there was a hump in there. So one of the first things I did was using a chainsaw. These are chainsaw files. This one I cut so I could put it in a drill press, putting that flat. Then I could run that down and grind in the drill press and grind the thing flat and have it flat. Yes. So that's what we did there. Then as far as the oil holes that I ended up with, I won't go through how I got there. It was, I think I've got 4 of these with all kinds of different holes. No, 3, and then 1 still pristine. So here is what I ended up with. And they're really quite small considering. I was a little worried at first they might be too small, that they'd clog with debris, but there was no sign of that at all. But here we've got the first one that relates to down here was 1/16 of an inch hole. This one I found I could eliminate totally. It didn't matter anymore. The next one here was 1/16. Then it became 5/64, so it's just increased a bit because now we're into that section in the middle here that's kind of in behind here where that hump was. So these 3 are 5/64. And then as we move back out to this back part here, then I'm back to 1/16 and 1/16. And again, these are approximate distances off of here. And just for those that are curious, the way I would decide where those holes were was I would stack these up, and if the hole were to go in here, I would lay the knife flat on the steel, score that surface. Then I would put on the appropriate friction, lay it flat, score there, same thing. And then I've got the 2 lines where I know the holes go between. So if anybody's interested, I'm just going to hold this up so a screenshot could be done, and hopefully it's clear enough. Okay. So, yes, you can see that I changed it quite a bit, and it was, took quite a number of times to do it. This is talking about a relic. Here I'm trying to shed oil because again, this initial area is flooded with oil because it's just spraying out from the thrust adapter there onto this surface. So this was getting always very soaked, and so I'd actually filed these troughs in there to hopefully get rid of some of the oil before it enters particular. Well, there's the one at the very bottom, which would have been getting lots of oil. Okay. Let's see here. Okay. Just a minute, I've got to gather my thoughts here from the notes. Oh yeah, just backing up a bit to talking about the slave cylinder when you pull your clutch in. The K13s came with a 34 millimeter wide piston. The K12s came with a 32. I put a K12 back on because when you pull the clutch in, your master cylinder has a defined quantity of fluid that it pushes down into the slave. Now, the wider that piston is, the less distance it's going to travel. So I wanted as much as possible, so I went with the old one, the 32. The smaller the piston, the greater amount of strength it needs to pull that clutch in. That's partly why I think BMW changed it. They got so many complaints. But I wanted the maximum amount of space. I wanted that 0.125 spacing here. Alrighty. Like I said, I'm not going to go into that. One of the things that I did find is this this arrangement here I mentioned in the other video is this is a Belleville washer, the same as this kind of thing. They're actually shaped like a spring, so when it's compressed, it does a desire to come back to where it was. And it has often been referred to, or is commonly referred to, as an anti-judder. And as I said in the other video, judder is really the uneven take-up of the group of steels and frictions. So it was sort of not really addressing the problem of oiling. It was just kind of hoping to cover it up, which it did. And it also slightly extended or people claimed it did. I couldn't tell the difference. The engagement or disengagement distance. One of the things I found for me personally was that I was getting a lot of oil on the top side. So a lot of oil was being delivered to the top here, even with my small hole. And that's because this is sort of like an on-ramp here. The oil would come out and there was a good amount directed upward. Well, I flipped it over, so therefore now the slope is directed down, and it was quite successful. I don't think it makes any difference to the functioning of this. This actually, if it were pushing on a steel, if it's this way, it's riding just at the base of these teeth. If it's in the way the factory installed, it's within this solid area. Personally, I don't think it makes a lot of difference. So that was one of the odd little things I did there, was just that I found did work. Okay. One of the other things that so the big problem here is getting the space allotment kind of between each of these plates and getting rid of oil. And one of the ideas BMW had at one time, and some of you have probably seen it, these little green rubber bands, they were referred to as, basically on these tabs, these out here, out this area. And they were there to help kind of push the plates apart. That was their goal. BMW gave up on it, but when I was kind of into this and trying to find out, I couldn't quite get it. Now that I'd got my oil down to what I thought, they still weren't breaking. So I actually went back to that idea, and I sourced these little O-rings. They had to be this high temperature stuff. And what BMW did is they put one of these green rings on one side and one on the other. So their idea was that it lifted the plate and there was a wobble back and forth like this. Initially, that's what I tried. I tried one on each side. Didn't help. And then I thought, okay, to help reinforce each other and their ability to push, now these, just back up, those O-rings have to be a specific thickness or in cross-section. Because what you want is it just proud of this steel, because the next one is going to be riding like that. And you want this to be able to be free under that. And sure enough, that's just resting there. It moves comfortably. So I did two on one side. And the idea there was, like I said, for these to reinforce each other. And it didn't feel like I needed to crack both sides. If you just cracked one side, remember this thing is spinning. So if you crack one side, the thing is going to wobble slightly, and that wobble will open it up. Whether that's true or not, the results those were the results. So as far as these rubber bands are concerned, I found that they were most effective on this one would be there, on the first two frictions. And what I did was I put this set here, and this other set would have been way around the other side. So there, I don't know if you can see that, there is a wobble going on there. And then after that, there are no bands. And a lot of that comes from, as we've seen, when you actuate the clutch, this moves out. So all these plates have to kind of jiggle and jostle themselves so that they're all even. Well, with this moving away, the group of frictions and steels here, that's really easy for them because it's right next door. But there's a accumulated kind of friction resistance for these deeper ones here that have to move. So that is the reason I'm assuming that I only needed these rubber bands on or O-rings on the lower two, just to kind of get it going, free up this area, and the rest did not need that. And they worked quite well. It took me a while to source these. I think they were in a place in Washington State. Anyways, they're probably other places. Let's see here, where am I? At some point I'm going to have to stop so I can break this video into two. I don't want to get into trouble with YouTube again. Okay, maybe I'll do that now, and then we can start another section. Okay.